we can get a polarized light by reflection as well. So let's consider these pictures. Okay, I think that you have seen this picture many times. When we have the incident beam, right, and then incident on the interface between the two medium 1 and medium 2. So some part of the light will be reflected to this direction, and some part will be reflected into this direction, right? And then we can use the Snell's law to find the relationship between the theta 1, the incident angle, and theta 2, the refracted angle here. So now, if I put something, okay, let's say that let me just put more details into this picture. So if we consider that if we have the unpolarized incident beam, okay, let me just say the unpolarized incident beam, it means that the electric field will will oscillate in many directions, right? As we have seen before. But then again, we can break the components of the electric field into the two components, to this component and then this component. So this component must be perpendicular to each other, okay, as you can see from this picture. Then again, we can just draw the two components of the electric field to be this one and this one, okay. So don't forget that we have these components. It means that the electric field is just oscillating in this direction, okay. And the other component is to be this dot. It means that the electric field is just oscillating in the into the page, out of the page, into the page, out of the page, etc. Okay. So this will be the oscillation of the electric field just into the two components, this one and this one. Okay. So when we have the unpolarized incident beam, right, just come to the interface, some part will be reflected, some part will be refracted, okay. In general case, the reflected beam is going to be the unpolarized as well, okay. And then the same for the refracted beam is going to be the unpolarized as well, okay. That's going to be in the general case. But then from the experiment by Brewster, okay, let me just talk about that one later. From the experiment by Brewster, he can see that if the angles between the reflected beam and the refracted beam equal to the 90 degree, okay, let me take a note here. If the angle between the reflected and the refracted light is 90 degree. So in this case, it's going to be 90 degree, right? Then the reflected light is polarized, okay. So that's going to be the results here. For example, if we have the unpolarized beam, okay, if we have the unpolarized beam incidence on this interface, but then after the incidence, the angle between the reflected beam and the reflected beam just making the 90 degree, okay. So it means that the reflected beam here is going to be the polarized light, okay. It is the polarized light, okay. And then so that's why you can see that it just oscillating in this direction, okay. It just oscillating in this direction, okay. But then how about the reflected beam, right? The reflected beam here is called the partially polarized light, okay. So what that it means by the partially polarized light, okay. So okay, let's go back and then look at this picture again. So now you can see that the electric field, right, for the unpolarized light will oscillating in all direction equally, okay. So I just want to say that in all direction equally here. It means that if we break the two components of the electric field to be this one and this one, right? So then this component and this component must have the same number or the same amplitude as well, or the same value as well, okay? Because electric field just oscillating in all direction equally, so that's why we just break the components. The electric field here must have the same value, okay? But now you can see that, just come back to this picture, if some amount of the electric field is taken off, so it means that the amount of electric field oscillating in this direction and in this direction will have the different values. So that's why I say that it's going to be the partially polarized light, okay? So then again, this angle, this incident angle, it has a name. So let me say that the incidence angle to make, okay, this phenomena, okay, so okay, so we use the theta p as a symbol, okay. The incident angle to make this phenomena is called, okay, is called the polarized with the polarizing angle, okay, just called the polarizing angle. And then or sometimes or just called the booster angles, okay, the polarizing angles or the booster angle here, it just means this theta p, the incident angle that we have these two beams making 90 degrees to each other, so it's called the polarizing angles or the booster angles here, okay. So now we just want to find the condition of this booster angles or the polarizing angle to have this phenomena. So okay, let's just start from the Snell's law. Okay, just start from the Snell's law. Okay, so from Snell's law it said that the n1 times the psi theta 1 equal to the n2 and then times the psi theta 2, right? So the n1 just be the refractive index of the first medium, and now theta 1 is the incident angle equal to the theta p. So we have the psi theta p here equal to the n2. N2 is the refractive index of the medium that the light transmitted to, right? So the n2 here, and now the psi theta 2. The theta 2 is going to be the refracted angle. But now you can see that if if this angle, right, equal to the 180 degree, okay, this angle equal to the 180 degree, right, this is 90 degree, it means that the theta p plus theta 2 equal to what? Equal to 90 degree, right? Okay, so let me take the note here. So with this we can get that the theta p and then plus theta 2 must be equal to the 90 degree. It means that the theta 2 must be equal to the 90 degree and then minus theta p, okay. So let's just write it down. We have 90 degree here and then minus the theta p is going to be equal to the theta 2. But then what is the psi 90 degree minus theta p? Is going to be equal to the cosine of the theta p, okay. So then when you just move the cosine theta p to the left hand side, so you will have the sine and then over the cosine, right, it's just equal to the tan. So then finally you will get the condition for the booster angle or the polarizing angle to be the sin theta p equal to the n2 and then over the n1. Okay, so this equation is called the booster's law, just called the booster law. Okay. One thing that I just want to mention is to get the polarizing angle right, or to get the polarization by the diffraction here, is not restrict from the small n to the large n, or from the large n to the small n. Okay, so it can be either way. It can just it can have from the n small to the n large, okay, or the n large to the n small. It can be either way. Okay, it's going to be different from the critical angle that we have learned in the previous chapter. Okay, because from the critical angle, it must be from the n large to the n small. It cannot occur from the n small to the n large. But now for polarization by reflection here, or from the booster laws here, okay, it can be either from the n small to the n large, or from the n large to the n small. Okay, examples. Light in the air. Okay, this light strikes a water surface at the polarizing angle. So this theta p is the polarizing angle. The path of the beam refracted into the water. Okay. Strikes a submerged slab of the material. So we have this material with refractive index equal to the 1.62. Okay. So now the light reflected from the upper surface of the slab is completely polarized. So we have this light to be polarized as well. Okay, so now we just want to find this angle theta between the water surface, okay, and then the surface of the slab. So let me just write down what the question gave to us. So we have refractive index of this medium, right, equal to n equal to the 1.62. Okay, but now for the water, we know that of the water equal to the 1.33, right? And then of the air, the refractive index equal to the 1. Okay, so initially we have the unpolarized light. Just incidence with the booster angle here. It means that the reflected light will be the polarized. Okay, and now the light just passing through, into the water, right? So this one just be the partially polarized light, the same as I mentioned here already. Okay, so this will be the partially polarized light, and then again, if you just incident with the booster angle, right? So it means that this light will be the polarized light. Okay, so then we just want to find this angle theta. So what's the idea? The idea for this type of the question is we need to find theta p first. Okay, if we can find the theta p, then we can find this refracted angle between the air and the water interface, right? If we can find this angle, so then we can find this angle just from the this light ray, right, and then the slab of the surface of this slab. Okay, if we can find this angle, then we can find this angle as well. Okay, and then finally we can just deduct to this one. Okay, let's do it. So the first part, let's find theta p. Okay, so now we say that from the air and then the water interface, right? From the air and the water interface, we have the tan theta p. Okay, we have the tan theta p equal to, from equation, the n2 over the n1. N2 is be the medium that the light passing through. N1 just be the medium that the light incident on, right? So it means that in this case, the N2 must be of the water and the N1 must be of the air. So we have the water to be the 1.33, right? and then of the air to be equal to 1. Okay, so then we can just solve for the theta p. We can get that the theta p equal to the 53 point, okay, 0.1 because we have the three same figures, right? 53.1 degree. That's going to be the theta p. So now if we know the theta p, we can find this refracted angle. Okay, we can find this refracted angle. So let's say that this angle to be let me use this color. Okay, so this angle is equal to the theta 2. Okay, so then from the Snell's law, right? From the Snell's law, it said that the n1 sine theta 1 equal to the n2 and then times the sine theta 2. The n1 is of the air, equal to 1. The sine theta 1 is the incident angle, right? Which is equal to the theta p. It's just the 53.1 degree. So we have the sine of the 53.1 degree equal to. So now for the n2, the n2 is of the water, just equal to the 1.33, and then times the sine theta 2. Okay, theta 2 is this angle, the refracted angle. So now we can just solve for the theta 2. Theta 2 is just equal to the 36.9 degree. That's going to be the theta 2 here. Okay, then let's find this angle. Let's say the theta. Let's find this angle. Let's say the alpha. Okay, so this is going to be the water, and then at the slab interface, right? Okay, so let's look at this triangle. You can see that this angle equal to the 90 degree, right? From this interface and then to the normal line here, equal to 90 degree. This one, the small one, is theta 2. This is alpha and this is theta. It means that if we combine this 1, 2, 3, 4, okay, 1, 2, 3, 4, if we combine this 4 together, it's going to be equal to the 180 degree, right? Okay, so let's do it. We have 180 degree equal to the theta plus the 90 degree, and then plus the theta 2, and then plus the alpha. Okay, so here we can get that the alpha is going to be equal to, okay, so we just move this everything here to the left hand side. It's going to be equal to the 90 degree and then minus the theta and then minus the theta 2. Theta 2 we know it already, equal to this one, right? But theta we don't know yet. Now let's consider this angle. Okay, so let's say that this is the theta p prime. Okay, theta p prime, because this angle is the crossing angle as well. So let me just use the theta p prime. It will not be the same as theta p. Okay, this will be the theta p prime. Then we can see that the theta p prime must be equal to the 90 degree, right? And then minus the alpha here. So we have the theta p prime equal to the 90 degree and then minus the alpha, which is equal to the theta plus theta 2, right? So now we can use the Brewster laws, right? To solve, to get the condition between the tan of the theta p prime and the refractive index between these two medium. Okay, so let's do it. Then from equation, the tan of the theta p prime, right, equal to, okay, n2 over the n1. n1 is for the incident light. So now for this interface, the incident light is for the water, and N2 is for the refracted light, which is the slab here. Okay, and we know that the slab we have refractive index equal to the 1.62, so we have the 1.62 of the slab, and then over for the incident one, which is the water, just 1.33, right? Then we can just plug in this into this equation. Then we can have that the tan of, okay, the theta and then plus the theta 2, right? Let me just plug in the theta 2. Theta 2 is the 36.9 degree, okay, equal to the 1.62 and then over the 1.33. So then finally we can just solve for the theta. The theta is equal to the 13.7 degree, and this is the answer. Okay, so this gonna be the all topics that you need to know in